All right, so today let me introduce this interesting paper in 2025, DeFoG, which is a discrete flow matching for graph generation, mainly molecular generation, large molecules. Because the small molecules like QM9 dataset, and then we have a zinc 250K, this is semi-large, not very large. Then Moses, then we have larger and larger data sets. And we are using discrete flow matching. We are using continuous time Markov chain. You know, a Markov process can either use a discrete state or continuous state. It can have continuous time or discrete time. And for any continuous time Markov chain, if you read the beautiful papers of Campbell in MIT, his paper in 2022, 2024, all of them I think NeurIPS, you will see how he represented this continuous time Markov chain for different applications like flow diffusion. So, for example, if you write the derivative of probability, it becomes divergence of rho PV. V is velocity, P is your probability. But in the discrete case, you can easily show that this becomes R transpose P. R is your rate matrix. You know, we have a forward rate, we have a backward. In the backward rate function, it is related to a term called denoising that you predict it with your GNN or your transformer. And this is the so this is the equivalent of the discrete nature, because in discrete space you go from one, and for example a carbon can become hydrogen, or so it's a state space. And this is so in terms of generator, it's very interesting to see. Then there are many ways to simulate your Markov process. But this paper is, again, as I said, is just using continuous time Markov chain and for application of just molecule generation. So graph generative models are essential across diverse scientific domains by capturing complex distributions over relational data. So graph diffusion models achieve superior performance but face inefficient sampling. That's why many papers like that famous paper, consistence models, and many different ideas, many paradigms have been created in the past just 2 or 3 years that to enhance this sampling by novel ideas. So because there is a tight coupling between training and sampling stage. In other words, or in other perspective, I can say there is I call it, some authors call it this exposure bias. There is a bias because the way that your training is done should be similar to the generation time. There shouldn't be any, because there is inefficiencies in the training. You always have error in machine learning, and it is accumulative, and you do in denoising several times. The same should be done on. That's why you need to have unrolling trajectories. That's why it is very computationally expensive, even the training. So this paper introduces DeFoG, which disentangles sampling from training. And how it does is based on discrete flow matching that respects inherent symmetries of graph as well. So they explicitly relate the training loss to sampling algorithm. That's it. So you see, this DeFoG enhances graph generation by introducing training sampling decoupling, which is an orthogonal improvement with graph iterative refinement models. So one node is selected. If you look at B, you see that here one node is selected to illustrate both noising and denoising, because if you learn it for just one node or one edge, then you understand everything. For noising, it follows a straight path from one hot of the clean to initial distribution. So for denoising, a network parameterized by theta predicts the marginal distribution of clean graph. There, the node's distribution is used to compute the rate matrix. So you need to know some background on marginal distribution. This paper, DFM Campbell, MIT in 2024, builds upon streamlined noising process. So the noising trajectory is defined just through simple linear interpolation starting from a chosen data point. In the denoising stage, it leverages continuous time Markov chain. As I said, you need a rate matrix. It is Z by Z. For example, you have 5, or let's say in DNA, let's say 7. You have 7 words, so it becomes 7 by 7. So what is the probability? For example, you go from A to T, or T to C, or C to G. All of these probabilities, you can encode it by R, the transition rate, by the rate matrix. And so it yields the probability that you transition. And the way we do this sampling, if I'm not wrong, is 1 over, it's exponential it's an exponential distribution that says to how much time you need to stay in a certain state. For example, how much time you stay in carbon as a node of a graph. For example, for 10 minutes, then for 2 minutes you go to, you should wait in another state, for example, in hydrogen. Or, for example, in language modeling, we say you stay in one word for some time, then after that you jump to another word in your vocabulary. So you can use it for any discrete data like language, graph, tabular data, and image segmentation, which is categorical. So it can be used for any application. So in 2024, under mild assumption, Campbell presented a closed form for a valid conditional rate matrix. By valid, I mean a matrix that verifies the corresponding Kolmogorov equation. Kolmogorov has forward equation and backward, like noising, denoising. And so you see, this is a very explicit closed form. And here, denominator is defined here. It's a cardinality of a set. And again, normalizing is performed so intuitively it applies a positive rate to states needing more mass than the current state. So it has an intuitive explanation as well. You need to know also about learning discrete flows over graphs. For graphs, we have nodes and edges. So you should multiply over all these probabilities to say what is the probability of graph given your initial or target. And for training, the rate matrix used in denoising steps require knowledge of marginal distributions. Each of these components consists of clear marginal distribution prediction. So because the computation is intractable, so we train a neural network to parameterize it. So we parameterize it. So simple. So you parameterize it, then the rest of that is just a cross entropy. And your cross entropy is like this. You have a lambda as well because you want to weigh nodes and edges differently to more flexibly capture varying topologies. Then they have a corollary that there is an upper bound on this difference, what you have learned and what is true on the rate matrix. So for training and sampling, if you look, is closely related. First of all, this extra feature is just modeling the let me say RRWP. This is relative random walk probabilities, which looks like this. For example, you have probability, for example, your transition matrix, in your adjacency matrix, then P, P2, P3, for example, how many walks do you want to walk? And then if it is PII, you concatenate with your node features. If it is PIJ, concatenate with. It's a very quick doing positional encoding instead of finding eigenvectors and those things. So again, H, when you find it, you also condition on that. Instead of noising without that, you are conditioned on that. And then find cross entropy. And then the same thing is happening for denoising. That's very interesting. So they talk about this design space of DeFoG, train distortion, train guidance, and stochasticity. Because orthogonal to target guidance, there also exists unexplored potential in design space of conditional rate matrices that preserve that Kolmogorov equation. They also talked about permutation invariance guarantees. For any permutation equivariant denoising neural network, the loss function is permutation invariant, and its sampling probability is permutation invariant. So they did experiments on Moses dataset and Guacamole dataset. They are very big, large molecules. We need some performance measures like validity, like FCD, uniqueness, novelty. And this is an example of different rate matrices that they used, because they satisfy the detailed balance condition.